So now we'll actually get started with chapter 14, which really addresses, really addresses three new functional groups as far as we're concerned: ethers, epoxides, and thiols. So what we're going to go through and do is look a little bit at the nomenclature for each of these. Remember, I'm not a big fan of nomenclature, and the nomenclature for each of these three actually doesn't fit very well in my little summary slide of all things nomenclature. Okay, so we're going to get some different rules as far as putting these together. We'll look a little bit at their reactivity, and then we'll also look at their synthesis. Some of these things you've already seen. For instance, we did talk about how we can make ethers. Okay? Those of you that have actually been showing up to office hours might actually know the name for how we make ethers. It's a named reaction known as the Williamson ether synthesis. Okay? There's other ways to make ethers as well, so we'll look at those two possibilities. The other one that you have probably already seen, the formation of epoxides. Okay? You should have seen that in your alkene chapter. How do we make epoxides? It's not a named reaction, but there's a particular reagent most commonly used. Not mercury for epoxides. Mercuration will actually work for ethers. Getting to the right idea, it's definitely an oxidizing agent. O3 will actually cleave your double bond completely open. To make epoxides, we're going to do an addition reaction using MCPBA or meta-chloroperbenzoic acid. Peroxybenzoic acid. I think that's right. Okay. And then the thiols, I highly doubt you'll ever see those ever again, really. We'll talk about a few of their kind of biologically relevant, interesting chemistry, but that's about it. So we're not going to get too much into the thiol chemistry. Along those biological lines, that last thiol, just out of curiosity, anybody know what kind of linkage that's known as? A disulfide bond, commonly seen. Nicely demonstrated for us by Zena, actually. Yeah, lucky you, huh? Curly hair. Curly hair is usually due to disulfide bonds within the individual hair molecules. So as it curls, it's curling because you're getting disulfide bonds in the hair linkage, bending back and causing that crimp. Okay, so it does show up in biology. That's really going to bug me. Is that bugging anybody else? Mm-hmm. Not being able to see the top?
Yeah. I think it's because the projector is too high.
We should be able to adjust the screen upwards, and I don't know why it's not pulling up. I will try my best to introduce other examples of where these things show up. Alcohols were really, really common because we had a lot of possible reactivity. Ethers, very related to alcohols in that we have that oxygen-carbon bond, except now we also have another carbon bond. So our ethers tend to show up fairly frequently as well in biology. In this case, you're seeing it highlighted in red in vitamin E. In the next compound, we have diethyl ether. Where have you seen diethyl ether before? Lab. It's very common for solvents. Okay? A lot of organic chemistry will involve ether solvents. Why do we use ether? Okay. As far as reactivity goes, we've reduced the reactivity on a lot of our ether compounds. We still have that kind of polarity within it. That oxygen is still partially negative, so it draws electron density away from the carbons, which makes our carbons partially positive. But we don't really have access to that chemistry very easily because those carbon chains to either side can freely rotate in the case of diethyl ether. And so anything that comes in and tries to coordinate with either the positive or negative can get smacked and knocked out of the way by the nonpolar tails. Okay? So we can expand the length of those tails to kind of decrease the polarity of that solvent or prevent that that oxygen's interaction. Conversely, if we can then somehow bind those nonpolar tails back, we can increase the polarity of the overall molecule. For instance, another common solvent used in organic chemistry Anybody know the name of this one? We have actually seen this compound. THF, tetrahydrofuran. That is also an ether compound. Again, very commonly used as a solvent. We saw it show up with your boron reactions, okay, when we're doing the alcohol addition reactions. Okay? THF happens to be much more polar than diethyl ether because the nonpolar carbons that are attached to our alcohol are tied back to the back side of that structure. That leaves the oxygen freely exposed at the other end, okay, which allows it to then hydrogen bond or be a hydrogen bond acceptor because it doesn't have a hydrogen, so it can't donate those. And that increases its overall polarity. So that's kind of nice with THF. We get low boiling points with our ether compounds. Why might that be important?
So if you're using it in the lab, you can know that you can boil it off before it's
Exactly right. When we run a reaction, we want to use a solvent that we can easily remove. Most of our products are what phase? Products? Really? Okay. For our Grignard reagent, the end of that was a recrystallization. Okay. We had a solid at the end. A lot of your products end up coming out as solids. Think into pharmacy. All the drugs that you typically, well, hopefully aren't taking that many drugs, but the drugs that we typically intake are usually also in a solid phase as well. To be able to isolate those solids, we need to have some way to separate them from something else. Our solvents are used in that case. We can dissolve the compound, do some separations, and then remove the solvent. And we'd be left with that solid behind. So we typically want a low boiling point. The other thing that's nice with our ether compounds is they are polar. We just addressed that with that partial negative oxygen. Okay? That polarity can be changed by changing the structure around a little bit, but we typically get some polarity associated with these solvents. The other big advantage when we look at our ethers is that they are aprotic solvents. Okay, why does that help? Well, if it was protic, that means we had something like an alcohol, a hydrogen out there. Why is that a problem? Okay, why could that be a problem? Instead of being an ether, we made that an alcohol. What happens to the chemistry? We can now do acid-base chemistry. So we would still have a polar solvent, and if we pick something like methanol or even ethanol, our boiling point is still relatively low, but we also increase the likelihood of other reactions occurring. Okay? We've exposed that oxygen a lot more, so it becomes more nucleophilic. Our hydrogen is also then floating out there for acid-base chemistry. Okay? So our ethers tend to give us the same kind of polarity and solubility and boiling point systems that we could pick up with our alcohols, but they also get rid of that acidic hydrogen, which helps things out. Okay? Last one that I put up there as an example for an ether, MTBE. I may have done that one but backwards. Maybe not. No, I did that right. Where is that commonly used? Or seen, maybe? Used to be used. Gasoline was used as an additive in gasoline. I don't remember exactly why it was used. Probably has something to do with controlling how clean it burns. Okay, so that ether is also used, or we use those ethers in different processes. Okay, so that's kind of the idea, that we do see these ethers show up everywhere, and what we're relying on is some of that polarity from our oxygen, but the minimization of our reactivity by adding on those carbon chains. Okay, so we get the solvation effects, but not the reactivity. Okay. We can then push this into a whole new category. We can look at something known as crown ethers. In the case of crown ethers, why do you think we might call them a crown? Okay. They're cyclic. Typically, where do we wear a crown? Our head, which is relatively round. Crown ethers do a good job of surrounding counterions. Okay? So if we go through and look at each of those crown ethers, thankfully we've got something highlighted in there. Where's our reactivity within the crown ethers? The oxygen. What's special about those oxygens as far as their reactivity goes? Any charges? They are partially negative. Why is that helpful? What did we identify? We have a possible nucleophile if we're going to push some hard chemistry. If we go a little bit softer, we also have a Lewis base. Okay? Those Lewis bases or even nucleophile capabilities can now coordinate with something positive. We can take advantage of that and have these crown ethers surround individual counterions, okay, which in general doesn't seem like that big of a deal. Let's see, did I just bring it up again? I didn't bring it up again. Okay? But it is actually pretty important to activate some different functionalities. If we wanted fluoride as a nucleophile, to get fluoride into a solution, we're looking at F minus, right? Well, we can't bring in just a straight up negative. So if we're going to add something that has negative, we're going to pick it out of the lab. It's not going to be F minus. It'll probably be with its counterion to stabilize that negative. So what's a good counterion? Maybe something like sodium, 1-for-1 exchange. Problem is fluoride is so small that that ionic bond is now much stronger and doesn't break, which means the fluoride can't go out and react as a nucleophile. So what we have to do is break the interaction between the sodium and fluoride. That's where our crown ethers can come in. We can design a crown ether that in its interior, we've got all of those partial negatives, which I'm just going to abbreviate as negatives in this case, all kind of pushing towards the middle. What can happen is we can then put in the middle of that a sodium ion. Right? That sodium ion is now strongly trapped or bound by the oxygens. Okay? Well, if the sodium ion now has all the electrons it needs, the fluoride can't share with it anymore. So now the fluoride has to go somewhere else. Now it can act as a nucleophile. Okay? So it's kind of a neat effect. What happens if we move up to something like the 15 crown 5? Okay? Now the interior of that has gotten bigger because we've added more atoms. The circle gets larger. Well, what happens when the circle gets larger? That just means, whoops, put the wrong one in the first one, didn't I? That just means we can now put a larger atom in there. So in the second one, you can see sodium. In our first one, I should have written lithium. What happens if we add more ethers? Jump up to the 18. We can now fit an even larger counterion in it. So depending on our source of our fluoride ion in this case, if we paired it up with a potassium or sodium or lithium, we could use a different ether solvent to then limit the effectiveness of that counterion and increase the reactivity of the fluoride because now it's not bound to that salt. Okay, so it's kind of neat in that respect. These types of compounds can be rather interesting. They are typically used in even larger structures to kind of trap metal ions. So you might see them to do other kind of interesting chemistries. They don't have to be oxygens necessarily. To be a crown ether, it has to be an oxygen, but you might see larger structures in this kind of crown system with other ions or other atoms acting as your ligands. Okay? So they're kind of neat in that respect, but that's about it. As far as naming goes, anybody see any patterns? What's the 12 stand for? Or the 15 or the 18? The number of atoms in the entire structure, followed by crown, and then the 4 standing for the number of our ligands holding it in, or our electronegative atoms. So in this case, our oxygens. So for our first one, we're at a 12 crown 4 ether. Next one, 15 crown 5 ether. Not that big of a deal to realize. Probably won't test you on that, and I doubt you'll see it again. Okay. But just something the textbook brought up. Thought it was kind of interesting. When we look at our ether nomenclature, it's a lot harder to summarize it in that red-blue blocks naming system that I put together. The red part is helpful because that at least gives us our priorities, and you'll notice where our ethers show up as far as priorities go. They're right at the very bottom of that list, just a step above halides. So if we have any other functional group in there, we won't name it as an ether. We'll name it based on one of the other functional groups. Okay? So, two primary ways to go through and name these. So that's one of the things that's also nice on this is that it may not match the blue box directions that we had before, but the new rules for naming these aren't that difficult either. So there's two ways. You've got your common name and you've got your IUPAC name. Okay? In the common name fashion, we'll take a look at our structure, and we're going to break it into the alkyl pieces. So if we look at those two alkyl pieces, what pieces do we have? How would you name those? Okay, we have ethyls. Okay. We can then arrange them alphabetically if necessary, or if they're repetitive, we can use our Greek prefixes to say di. We follow it up with the word ether. So in this case, we have ethyl ether or diethyl ether. Okay? What happens if we move to the other one? So let's name that one first before we look at IUPAC. What groups do we have now? You could pick the easy one. We got methyl, right? What about the other one? There you go, exactly right. We've got tert-butyl, also commonly seen as T-butyl. We've named our alkyl pieces. We can now arrange these alphabetically, and we would say T-butyl methyl ether. How come I didn't include the T? Or I did the alphabetical.
Prefixes don't matter for the alphabet.
Prefix isn't going to matter, so don't worry about that. We'll go based off of the B. B comes before M. Okay. Questions on the common names? Fairly straightforward. What happens when we jump to IUPAC? Okay, when we get to IUPAC, we're going to do a very similar process. We can name each portion, but we're not going to go with them as substituents. Okay, so in our common name practice, when we name each alkyl portion, we're going to refer to them as substituents. To make it a substituent, how do you know it's a substituent? So if we looked at this branch here, okay, we could name this as eth, which is ultimately all it is. It's referring to the two carbons. Why did we call it ethyl? The YL is your substituent name. Okay, if you're calling it a substituent, we can add the YL to our name. In the case of our common name, we're naming each alkyl portion as a substituent on our oxygen ether functional group, which is why we would call that first one diethyl ether. When we move to the IUPAC name, we're not going to refer to or break it up into those pieces. We're going to look at just the main name for it, or a shortened prefix name. So in each case for this, we would have F and F. We would then have to go through and decide between these two which one's the lower priority, which one's the higher priority. Okay, well, in this case, they're both the same, so it's not that big of a deal. So let's pick the one on the left to be our lower priority, and we will change it now to F-oxy. Okay, so our prefix oxy followed by what's the rest of our structure. Now this is our main chain. It's two carbons. What other functionalities do we have in that two carbon? Single bond, so it becomes ethane. Okay. Both names work. You'll quite likely see both show up on the exam, on any exam. For that structure that we've got drawn here, most people don't refer to that as ethoxyethane. Okay, why not? Diethyl ether was such a commonly used solvent that we typically use the common name. That's where our common names ultimately came from. Okay, they were just typically more or used more often before we came up with a standard naming system. Okay, What happens in the other case? What do we have? Same idea, figure out what our alkyl pieces are. This is where I'm going to break down on my nomenclature system. Give you the first one, it's easy. Meth. What's the other one? There are a couple names on this one, so I will go through and we'll look at all of those names as possibilities. Let's cross this one out for the moment so we know what we're looking at. I heard of prop. Prop is an absolute fair possibility. Is there another option? We go a little shorter. That's still a T-butyl. We could still go with T-but. Okay. If we go with prop, we have an extra issue. Where's our main chain? Okay. There's our main chain in the case of the prop name. Okay, which means we're going to have to be a little bit more careful with how we go through and name this. Okay, so we'll look at the prop in just a second. Let's go through and finalize our IUPAC with our common T-butyl version. Which is higher priority, our T-butyl or our methyl? T-butyl is our higher priority. So we would end our name with, go ahead and put this in as black, we get T-butane, and we have methoxy T-butane. Okay? So our meth is the lower priority, followed by our oxy. We've now got our full name. Okay? Questions on that version of it?
Is it a dash between the methoxy and the T?
Yeah, I just ran out of space. We should put a dash in there. Okay. Let's go back to the prop. We used our prop as our main name. So let's go through and name our substituents now on our propyl main chain. Okay. So we have this group as a substituent and this group. Okay. Which is the easiest to name of those two? We've got a methyl, and the other one would be still meth because we have one carbon, methoxy to specify that we have that oxygen there. So we have a methyl and a methoxy on our propane. Where is the methyl located? At what position?
2.
At our second carbon. Doesn't matter which way we count it. Where's our methoxy located? Position 2 again. As far as nomenclature, we got multiple choice. That's probably as far as I would go to name. I'd put those both possibilities up there and I'd look at my possible answers. To fully arrange this appropriately, let's see if I can do this right. I'm going to take a stab at it, and we would probably call this, looks to me like we would get 2-methoxy, 2-methyl, prop, whoops, no dash in there, prop what? Ane, no other functionality. Okay. Questions on that? So we're still following kind of our standard rules. We can either go through and use our common name and we just name each substituent and then call it an ether. So we're defining in the common name what we're saying our main chain is, the most important thing is the oxygen. So we're going to name every other piece around that oxygen. In the case of our IUPAC nomenclature system, what we've decided is that the main chain is the more important, or our longest carbon chain is the most important thing, not the oxygen. So we'll name based on our longest chain and then adjust our name accordingly. Okay? Questions about that? Yes?
So how would you know the methoxy before methyl?
It's alphabetically arranged. M-M-E-E-T-T-H-H-O-Y. O does come before Y. That's why we put the methoxy there. I could very easily be wrong on that. That whole which one comes first thing, I'm awful at. I'm not going to lie about that. So that's where I would reference the textbook, and that's one of the reasons why I think nomenclature is dumb. Both of those are going to get me to the exact same structure. Technically, only one arrangement is correct. Okay? Other questions with the nomenclature? Okay. Synthesis of ethers. How can we go through and make these? So when we're looking at a synthesis, what we're trying to do is make that compound. So we said there's two possible arrows we could look at. We could either look at it this case and say, okay, what did I make? Or what did I start with? Or the other option is we look at our double-headed arrow. So in one case we have a retro synthesis arrow, where we're looking backwards. Or we can look at our synthesis arrow, okay, which could just as easily be an equilibrium arrow too. Okay. So what would we need to do to be able to make an ether? What's going to be the easiest bond to make? So what do I mean by that? Well, let's draw on some other atoms. Would we expect our starting material to be something along these lines? Okay, with a negative charge out on that last carbon. Okay, why not? I'm going to react with H+. It's a ridiculously easy reaction, right? Why would I not expect that to be a valid synthesis for an ether?
Pretty unusual to have a negatively charged carbon.
Very unusual to have that negatively charged carbon. When we're trying to think of a synthesis, we want to think of the easiest bonds to make and break. Okay? To somehow get our current starting material, the one with the negatively charged oxygen, that is a ridiculously difficult bond to have broken off to begin with. Okay? Not a particularly feasible reverse step. What about if we'd done this? Negative charge there, and let's bring in a CH3.
Same situation.
Same situation. Not an easy bond to break. So what I'm asking you to identify your chemistries, look for the most electronegative atom, and look at what's connected to it. Which of those are feasible bonds to make or break? So when we go back, we're probably looking at breaking one of those carbon-oxygen bonds.
So could you have like a carbonyl and an alkene then?
Alkene's not going to be nucleophilic. So the carbonyl gives you a partial positive on the carbon of your carbonyl, which isn't going to drive a lot of chemistry towards that oxygen. It's going to drive more towards the carbon. So when we look at a carbonyl, we would typically classify that as an electrophile, not the greatest nucleophile. Okay, and we need the chemistry happening at the oxygen. Why at the oxygen? What charge would I put the best charges for across this bond? Negative on the oxygen. Why? Oxygen is more electronegative than the carbon. So the bond we're trying to make is that new bond. How we get those pieces is now our goal for our ether synthesis. Where did those pieces come from? Okay, where did our positive carbon come from? Where did our negative oxygen come from? So our oxygen, in the case of these, had to act as what? Had to act as a nucleophile. And our carbon acted as an electrophile. Now that we've identified some piece of information to it, we could now start to break through and come up with other options for getting this reaction to work. Okay? So that's kind of the next idea. So one thing, okay? Let's look at that negatively charged oxygen. Okay? Is that something we would typically just throw into solution? Hey, we got a negatively charged oxygen. No. Typically, we would get it from somewhere else. Where would we get it from? It's a nice easy bond that we could break away from that oxygen, so we get a negative oxygen. Put a hydrogen on there. Okay. We could put on a hydrogen, and I think, as I talked over you, you said another thing.
And on a metal, like you said,
We could-
to rip it off.
also do a metal. Both of those would be feasible options. If we did a metal, we'd be looking at a really strong nucleophile, because that oxygen would be formally negative. Or if we had the hydrogen, we'd have a weak nucleophile, because we actually have a bond now between those two atoms. So that addresses our alcohol side of it, or our oxygen side of it. What about the carbon side? How can we get that carbon to be positive?
You can do an halogen attached.
Halide's probably one of the easiest options. Are there other atoms that we could put on there? Is there another electronegative element? How about an oxygen? Oxygen would also make that carbon really positive. Okay. There's another possibility, which is probably the most difficult to see. I wrote that as CH2CH. Let's start to push another option. Where else could I get a positive carbon from? Not quite. There, you're getting to the right idea. You pushed it a little bit further than I wanted. We take a look at a pi bond. What's a resonance structure for that pi bond? We can push the electrons onto that leftmost carbon and it becomes negative. That's not what we wanted. What happened to the other carbon? Became positive. So what we're trying to do is find these pieces, these big bulk pieces, and that's what chapter 12 is about, breaking that easiest to make or break bond, and then come up with some way to connect. Okay? Think of other ways that you could generate that ion, that reactive species. Okay? So we could look at the synthesis of an ether via substitution. So that's the next trick on this. Each of those conditions would push a particular type of reaction. For instance, the very last one that we were talking about was looking at reacting an alkene. What kind of reaction would we do there? We react an alkene. What are our reaction types? Elimination, substitution, addition, acid base, redox. I'm not quite sure if I want to include that or not. It's probably, I'll go ahead and include it. I'll half include it because there's another one I want to include. Radical. Okay. If we start with a double bond, which reaction matches that? The addition reactions. Okay? So having an idea of what type of chemistry you need to do can help you whittle away at all the possible things that you had to go through and memorize, all those possible reagents. So if we're going to try and go through and make an ether versus substitution, we're going to do it acid catalyzed in this case. So what we're going to start with is our alcohol. Okay, that's what we said we wanted on one of them. And for our other one, where we're trying to get our positive carbon, okay, here's our partially positive carbon. And here's our partially negative oxygen. So what has to happen? We come up with some mechanistic arrows in this case. Something that might help identify your pieces here. Draw that oxygen. Draw on our carbons. Where's our new bond? Good, it's the one I haven't colored yet. Now dashed. Mechanistically, what has to happen?
You have to break the hydrogen bond on the top oxygen and then break the carbon bond on the bottom.
Let's go with simple first. Okay, you're right. We do have to break off that hydrogen, but if we break off that hydrogen, does that make this product? No. So let's focus on pushing towards the product as fast as we can first. Okay, so what would we have to do? Okay, if we break off the OH, that still doesn't make our product. We want to get as close to this product as possible in one step. It's still going to be wrong, but that's irrelevant. What bond needs to form? We need the carbon to oxygen bond. How do we make a bond?
Move electrons.
You need to move electrons. Where do we have electrons? On the oxygen. We have a lone pair on that oxygen. Move those electrons towards that carbon. What happens? Carbon has too many bonds, so we now have to evaluate and break the weakest or most polar bond. Do we have a weak polar bond? Carbon, oxygen, so let's go ahead and break it. What's the result? So this is what everybody hates doing, but I'm going to draw it out. Okay, so we get as a product our oxygen that still has a hydrogen, because I decided not to break that off yet, because that's not the most important bond to make. I'm going to focus on those making first. We've now made our bond to our carbon. Okay, so there's our two carbons now coming off, and we'd also have OH minus. What's the problem with this?
Oxygen has 3 bonds.
Sorry, what was that?
Oxygen has 3 bonds.
Oxygen has 3 bonds. It hasn't defied its octet rules, so that's not horrible. Okay, oxygen definitely doesn't want to have 3, and it doesn't want to be charged. So we would want to break a bond, and we could do that relatively quickly with that hydrogen that you were initially talking about removing. Okay, is there another issue?
The OH is stronger.
OH minus is a much stronger nucleophile than our alcohol starting. So what does that mean? The nucleophile immediately comes back, reacts with that carbon, and kicks out our alcohol that just was put on. What does that mean? Our reaction is not a nice simple equilibrium here. It's actually one that barely drives forward. Well, that's kind of crappy. We don't have our alcohol. So what we want to do is facilitate that somehow. How can we make that OH a worse leaving group?
Add a hydrogen.
We could make it acidic. We could add a hydrogen in our very first step. So instead of having our oxygen react right away, what we do is add an acid. Okay, this acid would generate H+, and in particular, it also needs to not generate what? What comes in with an acid? We can never add just H+. Name an acid. What about the conjugate base? You have the halogen. What's the issue with the halogen? It is its conjugate base. What's the problem with our halides? Strong nucleophiles. The acid we add must not have a conjugate base that is a nucleophile. What acid could we add? H2SO4. Okay? So we can add that acid. Now our oxygen can go pick up that hydrogen. Okay, what's the result now? Now we got to erase everything that we spent all that hard time drawing out. Okay, tough. Deal with it. Now when we go through and take a look at our structure, that oxygen is now positively charged. Does it want to be positively charged? No. So what does it do?
Breaks one of the oxygen hydrogen bonds.
It could break an oxygen-hydrogen bond, but then we push backwards. What's the other option? It could break our oxygen-carbon bond. But then we get a primary carbocation. That's not good, so what happens there? The lone pair from our other alcohol can now come in and react with our carbon. Now when we look at our product, we've got our oxygen, we've got our new bond to our blue carbon. Color coding this is ridiculous, by the way, for anybody that cares. Positive there, and we would have H2O as our leaving group. H2O is a nice, reasonable leaving group, not too bad. Does oxygen want to be positive? No, so what does it do? It's going to grab the electrons from the closest possible source possible. What's the result? There's our ether. Okay? You'll notice in the course of this reaction, we reacted to alcohols. What was our very first step? Activation of the alcohol, exactly like we did on Monday. Okay? To get our alcohols to react, we must pre-activate them and allow the reaction to occur. Okay? Do we have to do it in the presence of an acid? Okay, what happens if we did it as a base catalyzed reaction? So in this case, our starting alcohol is now bound to a metal. Let's pick something like sodium. Okay. What can you tell me about that oxygen-sodium bond? Very good answer. It's an ionic bond. The electrons in that bond spend all of their time with what atom? The oxygen. Does oxygen particularly want to be negative? Is that a stable thing? Nope. What can happen? That oxygen now needs to find something positive. Where is there something positive? The carbon. Okay. On our other structure, should have done that in black ink. How many bonds does that carbon now have? 5. So we have to break a polar bond. Do we have a polar bond to break? Yep. To the oxygen. What do we end up with? Our ether and OH minus. I thought OH minus was a bad leaving group. Could I acidify it? Could I put another hydrogen on that oxygen to help it act as a better leaving group? Should I put an extra hydrogen on our blue oxygen? No, why not?
Can we use the sodium in the initial?
Talk about that in a second. Why can I not put a hydrogen there? It's in a base solution. We cannot put a hydrogen on that oxygen right here because that would be a strong acid, or relatively strong. If we put in hydrogen there, we're saying we generate a strong acid in a base solution. That's not physically possible. Okay? So that doesn't fix it. So now we have to come up with another explanation for why that hydroxide comes off. We could go through and partner it with the sodium. How good of a job did the sodium do protecting our first O minus? Not a very good job. Okay, so that's kind of odd. Why does this reaction work? So is this, which is ultimately our answer. OH minus is a bad leaving group, but what's it leaving into? It's leaving into a solution that is equally bad. Okay? So we are in a massively equilibrium, that makes sense, right? Adverb describing a noun. Okay, no English majors, that's okay. We're in an equilibrium reaction. How can we drive this towards our product? What do we know about our ether products? What's their boiling points? They're very, very low. Our alcohols, on the other hand, much higher boiling points. So what could we do to drive our product formation? Distill it as we react it. The ether boils off, our alcohol is left behind. If we get rid of the product, which way does the equilibrium shift? Towards our products, and we end up generating more. Okay? Why would we pick a base reaction over the acid reaction? Comes back to the possible materials that you can pull out of this. If we take a look at our acid reaction, we had to have the exact same alcohols as our starting materials. We couldn't do a pre-reaction to generate an acidic leaving group and allow that to then shift across. Okay, that doesn't work. Okay, if we move to the base catalyzed one, how do we generate this species to start with, our nucleophilic oxygen? We can start with whatever alcohol solution we want. Let's say it's the butyl one, or T-butyl, and we add what reagent? Goes back to testing your chemistry. What reagent allows for this reaction to occur? What type of reaction is it? On our far left, So I heard two answers, a substitution and an acid base. On our far left, it's acid base. When we move down into the meat of this reaction down in here, that's our substitution. Okay? How do we do an acid-base reaction? What do we need? You need an acid. What's our alcohol? An acid. What else do we need? A base. What base do we use to react with alcohol so that we can get a negatively charged oxygen in a reasonable quantity? Sodium metal or sodium hydride. So we can string together our base reactions to generate ethers in such a way that we can generate non-symmetric ethers. Whereas in our first case, the acid catalyzed, we have to get symmetrical ethers. The carbon groups on both sides are going to be identical. We can't qualify or generate enough of a difference in that reaction to support the formation of only one type of ether. Okay? And our base catalyzed, we can get that unsymmetric one. So it's a pretty huge difference, which is why the Williamson ether synthesis, base catalyzed synthesis, gets the name Williamson, because he was able to make the unsymmetric ethers. Okay? Other ways to make ethers, we can do an addition reaction. This chemistry comes back to that mercury ion. When we went through and looked at this really quickly before, we had a couple options for what we could add as our nucleophile. Okay, in this case, we're looking at that ROH being our our ether former. That's our nucleophile. We have also seen it where it was H2O. What functional group do we get if we add H2O? We get an alcohol instead of the ether. Okay, quickly how the reaction works. Mercury will release one of the acetate groups because those are really good leaving groups. So OAC is the same thing as that oxygen structure drawn there. In the process of doing so, that mercury becomes positively charged. Are there electrons available somewhere? In, say, our alkene, which can come in and react. The result of that is we then end up with, whoops, no double bond in the middle. That was my bad. We end up with what is known as the mercuronium ion. Mercury is so large that as the double bond comes out and reacts, the lone pairs on that mercury go right back towards our most positive carbon in that structure to form the mercuronium ion. This is then followed by our nucleophile attacking the most positive position, which happens to be
Mercury.
Mercury is positive, but it's not electrophilic. So where's our most electrophilic position? Mercury is a great leaving group. We'll attack the most substituted position because the mercury is a good leaving group, kicking that out. We end up with the mercury oxide complex. The mercury can be removed using our sodium borohydride. Okay, and we'd end up with our final substitution. Okay, so as far as how this ends up coming together, our regiochemistry, we get the Markovnikov addition. Our hydrogen atom at the end of this reaction goes to the position that has the most hydrogens to start with. So we'll go ahead and draw in the product. Whoops. There's an OR. We'd have our hydrogens here. Okay. What's nice about this method as well as the base method? Both can generate unsymmetric ethers. So that's kind of cool. Instead of calling it the anti-Markovnikov, we'll stick with non-Markovnikov. Blah, blah, blah. Okay. $55, right?
37.
go. Reactions of ethers. Okay, what did we say was reactive on the ether? We've got our partially negative oxygen. We do have the partially positive carbons. But those are only reactive assuming that we can get the oxygen to take the electrons away. So what we'll have to do is go through again and activate our oxygen to get it to turn into a good leaving group. We can do that with something like a strong acid, say HBr. This should look really, really familiar to you. The electrons can kick over. We'll kick out the bromide. We've now activated our alcohol. And we have a positively charged oxygen. And we have our bromide. What can happen now? Bromide will do a nucleophilic attack at our most electrophilic position, which happens to not be the most positive, because our most positive appears to be that oxygen. Where's our most nucleophilic? The carbons to either side. Which carbon is more nucleophilic? That's a very hard question to answer. So just like on that test question or that quiz question yesterday, both are possible options. What will end up happening is we will do that acid-base reaction with the alcohol, end up doing it twice in the presence of HBr, okay, particularly in excess. And what do we get? We'll end up with our ring, our alkyl, and we'll have water. There's a reason I left off the bromine on our ring. Okay, that bromine is bound to the ring. How is it bound to the ring? Okay, should I just draw a straight line? Ooh, actually, we can get away with a straight line. That was my fault. We should be aware of the stereochemistry implications. This is an SN2 type reaction, which would suggest that bromine should come in from the backside of that bond, which means in our answer the bromine should be, where's the backside of a bond aimed away? Coming out at you. Okay? Why do we not have to specify the stereochemistry? Should that bond have been dashed to begin with? No, it's not a stereocenter. Okay? So it didn't matter if we put in a wedge or a dash, technically. Okay? So evaluate stereochemistry, do a better job than I did, make sure that the wedges and the dashes are actually there for a reason. If they aren't there for a reason, then you don't have to stress about them. Okay? It's there only to confuse you. So don't let it confuse you and move on. Okay? Questions about that? Okay. Last thing that I'll add, the little last thing at the bottom there says read about the oxygen radical reaction. Your textbook talks about how peroxides can react with ethers. It's one of the reasons why when you buy ether, it typically comes with an peroxide inhibitor to prevent an oxidation reaction. And that's because if peroxides form in that ether solution, they tend to generate explosive products. Those explosive products are not particularly fun when you're trying to work with a flammable substance. Okay? So they usually add an inhibitor to them. If you were going to use diethyl ether in a lab, you would probably distill it because when you purchased it, it came with that radical inhibitor, and you'd then want to get rid of it by distilling your ether across, leaving the inhibitor behind. Okay? Or reacting it with something else. So when we do lab, the Grignard lab next week, take a look at the ether bottle if we still have it. It doesn't say it's just diethyl ether. It actually tells you that there's an inhibitor in it. What's the problem with inhibitors? If you want a solvent, all you want is that one solvent. What happens if there's something else present?
It's not as pure.
It's not as pure, which means it could mess with your reaction. All right, we want to limit our exposure on that. Okay. Here's the reason why I was racing through it as fast as possible. Another quick quiz. I need to talk a hell of a lot faster than I am doing. See how far you guys get with the quiz. See what happens as far as time. Might talk a little bit more about epoxides, but not a whole lot. Probably won't even get into reactions. So I will give you 5 minutes. She'll give me 5 minutes to talk.